Hey guys, this is Taylor and today we are solving the problem number 3620, which is network recovery pathways. And this is from the bi-weekly contest 161 and this is third problem of the contest. Okay, let's start. So you are given a directed acyclic graph of n nodes, okay? Note this, directed acyclic graph numbered from 0 to n minus 1, represented by 2D array edges where edges are UV cost, indicates one-way communication, okay, with a recovery cost of cost I. Some nodes may be offline. You are given a Boolean array online, where online I equal to true means node I is online, and node 0 and n minus 1 will always be online. And a path from 0 to n minus 1 is valid if all intermediate nodes are online and total recovery cost on the path does not exceed k. Okay. For each valid path, define its score as the minimum edge cost along that path, and I need to return the maximum path score, the largest minimum edge cost among all valid paths. And if no path exists, I need to return -1. Okay, so let's see what is given to us and how we'll be solving this. So we have given some graph like this. Inside that graph, we have some nodes as offline. So whatever paths going to that node, that path will be invalid. So I can simply do this thing while I will create the adjacency listener. I will just ignore this thing. Like if any offline node is involved. So this part I will simply avoid. I can simply avoid. Now next thing is given to us is k equal to 12. So let's see what is that means. So what is the path from 0 to n minus 1? So there are 1, 2, 3, 4, 5 nodes. So n minus 1 will be 4. So this is our target node. This is our source node. And we have to find path from source to target. So, okay, let's try to find all path. So this is my first path, this one and this one. So what is the minimum cost along this path? This is 6, this is 6. So minimum is 6. Okay. So let me write 6 here. Okay. This is for path 1. Superb. Now second path. Second path, I think this is the second path. Okay. So what is the minimum node here? This is 5, this is 7. So I think minimum is 7. Okay. Sorry. Minimum is 5. Okay. Now I need to calculate the sum as well. So what is the sum along the path? So for this 6 plus 6, the sum is 12. And for this 7 plus 5, for the second part, sum is equal to again 12. And my k is equal to 12. So this sum is not exceeding this k. I mean, that means that both paths are valid. This path 1 is valid, path 2 is valid. Now what I need to figure out, what I need to find, I just need to return the maximum of this minimum. So 5, 6 and 5. What is the maximum answer? 6. So my answer will become 6. Let's check. Yes, answer is 6. Okay. So this is basically that question. The question is little lengthy. So if you don't get it, don't worry. I think this explanation will help you. So I hope that is clear to you what we have to find out. If you have to like try run for one more case. So this is our source node. This is our target node. Okay. Now we have to check the valid paths. So this is 3. This is 4. Okay. So total cost is 7. My k is 10. Okay. It is valid path. So what is the minimum cost along this? 3. 3 is the minimum cost. So I will just write 3 here. Okay. Now I will go here. This is 5, this is 10, this is 15. Okay, but 15 is exceeding this k. Okay, so I can't consider this path. So let's say our k is 20. Okay, in that case I will consider this, for example, just to understand. So what is the minimum cost here? 5 is minimum cost, right? So 5 is minimum cost. What is the maximum among these two? 5 is the maximum, right? So my answer will become 5 here in that case. If the k is equal to 20. But in that case, k equals to 10. So this path will be invalid. So I am only having this path. And what is the minimum node here? 3. And if 3 is the only minimum node, what is the maximum of this? 3 is the answer. So I hope you got it, what we have to do. Now, how we can solve this problem? So the very first thing comes to my mind, the brute force approaches. So what I will do, I will just try to go, I will start from here and I will try to explore all the paths. I will try to explore all the paths and I will keep track of minimum every time. So this I will not consider definitely, but I will keep track of this. I will keep track of the minimum. This is telling me 6 is a minimum. This is telling me 5 is a minimum. So 6 comma 5, I will return the maximum of this. So 6 will be my answer. So this is the brute force approach and it will definitely not work. So if you see the constraints, so we have constraints like our edges length is 10 to the power 5. So how many edges we can have? 10 to the power 5. So these are just number of edges. And among like out of this number of edges, how many paths we can have? It's definitely a very huge number. We can have very huge amount of paths we can have. So definitely this brute force will not work. So first I tried the brute force approach only using DFS. So I was trying to go to every path and I was keep tracking of the minimum. And if that minimum is satisfying the condition of the sum addition k wala thing, then I was just going it like this. But this will not work. So how we can solve this problem? So just to get a little hint from the question. So we had given here cost equal to 10 to the power 9, and second thing is given to us is this k is 10 to the power 13. Okay, these two things. Now let's check one more thing. So here we have given return the maximum path is for largest minimum. Okay, so whenever we got anything like we have to minimize the maximum or maximize the minimum, and we have constraints like this, like 10 to the power 9, 10 to the power 13. So you can think of a binary search solution in those cases. So binary search solutions are little different than normal DFS traversals and all. So you don't need to think of the path in terms of path. If you have to think for a binary search solution, so in binary search we have to think in terms of answer, whether 7 can be my answer, whether 10 can be my answer, whether 50 can be my answer. You have to think in terms of that. Let's see how we can think in terms of that. So I hope that is everything is clear till now. Let me know if you have any doubts. So for this graph, let me redraw it. So I have this clean diagram now. Now we have to do something in terms of binary search, right? So let's see how we will be doing this. So let's say like binary search, our mid came something like this. So my mid came, let's say 6. Okay. Now what I will be doing? I will be checking whether this mate is possible in this path or not. So I will be like for now I will be exploring all the paths and I will be checking whether that is correct or not. Let's see. So I'm starting from here. I will go here. So my path length is 6. Okay. So I can definitely consider it. I will go here. Now I will try to move towards 4. I will go here. I will see it's again 6. Okay. So what is the minimum cost among these two? It's 6 only. Super. And what is the sum? It's 12, and which is allowed. So I can this 6 is possible. This 6 is possible. Okay. Let's try to like improve something. Let's try to go for 7. Okay. Okay. Let's see. So I will be starting from here. This is 7. Okay, super, no issue. But as soon as I reached here, I can see here I got the 5, right? So this 5 is something which can cause the issue. If my answer is 7, if my mid is 7, then this 5 I can't consider. So let's take an easy example and try to understand what I am trying to say. So here I have drawn one graph. So here I am having this is source node, this is target node, and we'll try to reach this. So let's say our k is 20. So what is the path given to us? 7 plus 5, 12 plus 3, 15. So 15 is definitely satisfying the condition. 20, yes, it is satisfying. Now what is the minimum cost among this? So I think 3, and 3 will be my answer because there is no other path. So definitely 3 will be my answer. Now I want you to make one observation here. Okay, that observation will help you in solving this whole problem. That observation is, so 3 is the minimum cost here, right? In this path, can I see any edge which is less than 3? Can I see this? No, right? So the answer lies behind this only. If 3 is the answer, then I can't get any age which is less than 3, right? So all lengths either will be equal to 3 or it will be greater than 3. Okay, I can have equal to, that will not be an issue. But if less than, so that will not be possible. So what I will be checking here. So roughly if I say you, if we don't go in very detail, roughly what I will be doing. So I will be iterating over, let's say my possible key value is, let's say 100, for example. So I will be going from 0 to 100 in binary search, and I will be trying to somehow iterate to this graph. I will try to iterate in paths considering ages. Can ignore this part, greater than equal to my mid, binary search mid, this thing. Why we are doing this? Because I'm considering that if, let's say, I'm having this mid is my answer. So how this mid can be my answer? When my binary search, how this mid can be answered? When this path contains all the edges which are either greater than or equal to that age. I hope that is clear why we are using this age is greater than equal to mid. So what I will be doing, let me again explain. So I will be taking one mid from here. Okay, I will be exploring all the paths, but that path should have one condition. The path should be greater than or equal to mid, greater than or equal to mid. Okay, and if that is not mid, so let's say if my mid is, let's say, 7, so if as soon as I got here, I will discard this path and I will not move here. I'll try to move here because this is 7. So I hope that is clear. Now let's see how we can solve this problem. So this is the first part of binary search, and that is pretty easy. Next part is also easy. Let's see. So let me write down this. So first thing I need to do, binary search on answer and check all paths. Okay. So how I will be checking all paths? So to check all paths, I have two ways to check the whole paths. The first A option is topological sorting. Topological sorted order. Second part is Dijkstra algorithm order. Dijkstra. Okay, so we have these two approaches to solve the problem. The first way is either I can use topological sort order or either I can use Dijkstra. Now let's see what these two algorithms do. So if we talk about this TopoSort algorithm, what it gives. So the first thing is it works on nodes, right? It works on nodes, and it gives me something like sorted order. So it will give me some X, Y, Z, A, B, C, some nodes, right? And that will be some order which can be easily iterate, which can be easily passed through using the directed acyclic graph. In directed acyclic graph, I can easily traverse. The better word is traverse. So in directed acyclic graph, I can easily traverse through this topological sorted order. Second thing is Dijkstra algorithm. So what Dijkstra do is it tries to get the shortest path, right? Shortest path from source to target, and that will be depend on the current graph condition. Okay, current graph condition. So what I will be doing is, if I will be using this Dijkstra algorithm now, so my graph condition will change dynamically every time. Why? So let's say my mid is, let's say, 50. So what I will be doing, I will be eliminating all the ages which are less than 50, right? I'll be only considering ages from 50, 51, 52, 53, and so on till the constraint. And every time. Let's say next time my mid becomes 75. So what I'll be doing, I will be eliminating all the ages which are less than. I will not consider them. I will only consider these. So according to this, this graph will every time change. So I need to again and again compute. I need to again and again find the shortest path. But in case of topological sort, if I get topological sorted order once, okay, if I get this thing once, I can definitely reuse it. How I will be reusing it? So these are based on the nodes, right? So I will say, okay, I need to iterate X. What all adjacent it is having. If adjacent weight is greater than that age, then I will explore it. Otherwise, I will not explore it. In that terms, I will try to find the path of the last node. Okay, and in the end of the day I will check whether the distance of my last node, okay, last node is less than equal to k, then my answer can be possible using that made of binary search, otherwise it will not be possible. So I hope you got some idea what we'll be doing. Let me quickly summarize it, what we'll be doing. So I will write a very rough pseudocode. Okay, so not pseudocode, basically the approach, what we'll be doing. So let's say we will call binary search first thing. We get mid, let's say our mid is 50. Okay, now I will consider that I am having the topological sorted order already exist. I will find out in advance that thing. So considering I have TopoSort order. Okay. So what is the next thing I need to do? I need to explore all nodes in TopoSort and try to find minimum distance from source to last node or target, we can say. So what we are doing in this toposort, let's try to understand. So binary search will give me mid in like according to that mid, I will basically I'm having toposort order already exists. Okay, so let's say my toposort order 20, 10, 20, 30, some nodes. Okay, and so I will be going to 10. I will be telling what all ages you have. You are connected to 20. With what value? It will say 50. Then yes, I will consider. If it will say, okay, I am connected to 30 as well, but with 25, I will not consider. That way. If let's say this 20 is again connected to 40, it will say, okay, with what value? It will say, let's say 50 again. So my path is 100. My distance to reach 40 is 100. I will definitely directly check whether this distance is less than equal to k. So let's say our k is, let's say, 120. So yes, it is less than. So definitely my 50 can be my answer. I'm not sure here in binary research whether this can be my final answer or not. But I can consider this 50 can be my answer. I can try to get better. I will try to get better than this. So I will I will set the low as mid plus one, right? So that will go in deep in binary search. But just to give you an idea why we are doing certain things, so I hope you guys are having pretty clear idea. I've explained it twice, thrice. So if you still have doubt, please feel free to comment and we can discuss on this. So let's try to write some pseudocode on this. So the pseudocode can be little large, so let's quickly write it in little compact manner. So basically, typically we have to do only four things. First thing is create adjacency list. Second thing is find topo sort order. Third thing is using this topo sort order, uh, find check. It should be check whether current made current made of binary search can be a valid answer. And the last thing is binary search on the answer. Okay, so this will go like this. So first of all, very first thing, I will create the adjacency list. Okay, very first thing. Second thing is I will create a TopoSort order. Okay, this will be my first thing. Second thing. Now I will jump on here. I will try to get some mid. Okay, and using this mid and this topological sort order, I will try to find whether that answer is yes or no. If that answer is yes, I will try to move towards right. If that answer is no, I will try to move towards left. So that's how binary search works, right? We have with the here we have low, here we have high, and accordingly, if true and false, we move either right, either false. So the same thing we will be doing here. So let's try to quickly wrote what adjacency list will how we will be creating this. So I'm writing code for first part. Okay. So we'll be just iterating over this pages. In ages, what I need to do, I need to create some adjacency list. Okay, this will be empty for now, and I will write something like this: adjacency list of u dot append. I can append definitely a v comma w. Okay, so what this will say, and I need to add one condition here. That condition will be if u and we are online. If any one of them is offline, I will not go and add the age. The only condition is both should be online. Then only I will be doing this. So first thing is done. Okay, let's try to find the topper sort of this. So just to find the topological sort, what I need to do, what I need to have. So let's take one example. Let me draw an example graph here. So I have drawn this graph here just to let you revise what is topological sorting and all. So what I will be doing every time I will be checking what is the node which is having 0 degree. So I will definitely start from 0 anyways. So 0 is having 0 degree. I will try to remove this node. I will try to remove this node. I will just free up this node. So I will just decrease these nodes as 0 and 0, and I will add 0 in my topological sorted order. Super. So this 1 and 2 are in, let's say, 0 and 0. Okay, I can store it in queue. Okay, so very first thing 0 was in my queue. I will pop it. I will just iterate and free all over these edges. I am having this edge is removed, so I can decrement this 1 to 0. This edge is removed, so I can decrement one edge, which is 0. Okay. Now, how many edges are how many in degrees 0? So 1 is also having 0. I will pop this out. I'll try to remove this edge. So if I remove this edge, this will become 1. And as soon as I popped it, I can insert in my answer. Okay. Now, okay, next thing, 2, I will pop 2. Okay. So as soon as I pop 2, I will add it here. Next thing, what I will be doing, I will be removing the edge. Okay. Now I can definitely reduce this to 0 because it's reaching 3. So here I got 3. I can add it here. Super. Now let's see. So I can remove this 3, and 3 is not targeting to any node. So definitely I can insert it, add it here, and that will be fine. So this is the topological sorting, and for this topological sorting, what I should be having. So in starting you saw, right? I was having something like this: 0, 1, 2, 3, the in degree array. If you remember the in degree array, what this in degree array will say, how many edges are coming to 0, 0. How many edges are coming inside 1? So it is 1. How many edges are coming inside 2? 1. How many edges are coming inside 3? It's 2, right? So this is my basically this will help me find the topological sorting order. So let me remove this part. I hope this much is enough to revise this. Let me copy this quickly and put it here. Okay. So how I will efficiently calculate the integer array. So I know one thing, that this V is basically target, right? So I will definitely define something like this in degree here itself. Okay. In degree of, I will initialize all values with 0 into n. Whatever I'm having, I will be initialized with n empty zeros. and I will be doing something like this in degree of vertex b plus plus, something like this. That way I can simply efficiently initialize. So my in degree array is ready. Now I need to find the topological sorting, right? What I will be doing to find topological sorting. So I will be adding all the elements. I will be defining, first of all, I will be defining some queue, and I will be adding all the elements in the queue whose in degrees are 0. So let's quickly iterate over the indexes. For node, yes, let's write little clean. For node in range, I'm having nodes from 0 to n, right? So I will be writing from 0 to n minus 1. Okay. Now what I need to do? If in degree equal to 0 of that node I, of that node, then what I need to do, I need to insert into the queue, queue dot append node. Super. Now next thing I need to do, so I need to iterate over, I can store some TopoSort order. I can initialize it with an empty array. Okay. Now why my queue is not empty? What I need to do? As soon as I pop some node here, node equal to queue dot pop. As soon as I pop something here, I will add it in answer. Topo answer, let's say, for now, dot append my current node. Superb. And I need to iterate over all the neighbors. For neighbors, in adjacency list of that node, I'll be iterating over all the neighbors, let's say 0. So 1, 2, 3. I'll be iterating all over the, and I will be removing the integers, right? So in degree of neighbor minus minus. Okay. And the next thing that I need to do is, if in degree of neighbor equal to 0, then what I can do, I can definitely add it in queue dot append neighbor. So that way I will easily keep tracking of the neighbors of the nodes which having 0 in degree. So I will quickly append it to queue so that this can become my next node to iterate. Superb. So that way in the last I will just return the TopoSort order. Okay. My second task is also done. This one is done. This one is done. Now I need to implement the binary search. Let's try to do it. So I will be writing something like dev binary search. Okay. And I will be defining something like low equal to 0, high equal to what is the high? So we will be taking two things, minimum of k, comma. So we have ages, right? So we have this graph, we have ages. And I know one thing for sure, that my answer can't exceed k. Okay, because k is the sum, total sum that I will be having. Second thing is what, my answer can't exceed the nodes present here. Okay, so if let's say this node is having 10 to the power 6 value and k is also 10 to the power 6, so my answer can't exceed that, right? My high, the maximum, because I am focusing on the finding this node value, right? So I will be writing the max age. Wait, I can write something like this. And I need to consider k as well. So let's say my k is, let's say in some certain scenario, my k is less. Let's say my age weights are 1, 2, 3, 4, and my k is already 0 only. So in that case, my answer should be -1. So just to make sure that I don't iterate over this, I need to consider k here as well. Otherwise, I will only consider this. So how I will be writing the binary search, while low is less than equal to high. Why I'm writing high here? Don't know. So mid will be low plus I minus low divide by 2 if if correct order, if I will be calling this function, if let's say fun for now, function of mid is true, then I can definitely shift my low towards mid plus 1. Otherwise I can shift my high to mid minus 1. So what? So in the end of the day, I can directly return low minus 1. We will see in the code why we are returning this low minus 1. But for now, let's consider it. So now only third thing is remaining, which is basically iterate over the TopoSort order, and I will be checking whether my node value is correct or not. I mean correct mid is correct or not. It can be a valid answer or not. Okay, so let's try to write that code. So I'll be writing fun here for now. We will write a better name in our code. So I will be having access to mid, okay? And I will be having the access to topological order as well. Topo order. What I need to do? I need to iterate over this topo order. And before that, I need to keep track of distances also. So I will be checking, let's say 0, 1, 2, 3. And there are 4 nodes. So current on the zeroth node will be having the zero distance. All nodes will be having infinite distance. I will try to check what is the minimum distance I can reach till 3. What is the minimum distance required to reach 3 using this top order? Okay, so let's try to see. So I will be quickly defining my distance array, something like this, infinite, okay, infinite n times, and I will write something like distance of 0 equal to 0. Why? Because initial distance, I will be starting from 0. Now let's start. So for node in top order, so my first node will be definitely 0 in top order. I don't need to worry about that because that is the start node, that is the leftmost, that is the start node of my graph. So I will try to check uh, if I will try to iterate over the edges, neighbors. For neighbor in adjacency list of node, I will try to see whether that neighbor's age, or here I am having access to cost as well. So whether that whether that cost is greater than or equal to, is this mid or not? Otherwise, I will not consider. So if cost is greater than equal to mid, then only I will update. So distance of neighbor equal to minimum of. If I am having better option, then only I will update, right? So what I will be doing? So distance of node plus this cost, comma, distance of neighbor. So if this distance of neighbor already contains something as minimum, then I will not update, otherwise I will update. Okay, so if that condition is met, we can definitely go and do something like that. And in the last, if distance of last node is less than equal to k, then I can return true, that this can be my valid answer, else return false. So I know there is lot of things here. So I prefer to explain a dry run for this all 4 parts. So I will be attaching part 2 of this video in the description, you can check. So in that part we will just do a dry run, just do a clean dry run for all the 4 parts, for all this function, this function, this function, and this function, so that we can better understand. And then after watching that part 2, just try to move to the code and try to go to write the code yourself, and I will be also writing code for you. So With that, we let's wrap up this video because it got already very long. So thank you very much for watching this video. And in part two, we'll be doing two things. First thing is we will be dry running on the one test case, all these four parts, and second thing is we will be writing code. So thank you very much, guys.